Okay, today we'll be doing 24 rigorous limit proof, and of course we'll be doing them in one take. And I have a file in the description for all the questions, and make sure you also know the 4 rigorous limit definitions in the previous video. And after this video, you will be much more comfortable for your university level calculus class or real analysis class when you have to write a proof for limits. So with all that being said, let's get started with number 1. We have the limit as x approaching 4 of 2x minus 3 is equal to 5. And this is how I like to remember. 5 is finite. Likewise, this 4 is finite. This is the typical epsilon-delta definition. Later on, we'll be dealing with some infinity here or infinity here, so make sure you know all the difference. Again, check out the previous video with all the definitions that you should know before this video. So, I'm just going to write down the proofs. Firstly, of course, write down PF. And for all this, the 4 words will help you. Given, choose, suppose, check. Here will be given, again, because 5 is finite, so we'll say given epsilon greater than 0, and then second word is choose. We'll be using delta because 4 is finite. Choose delta to be something that I don't know yet, so I'm just going to leave it for now. And then we are going to suppose, okay, x is approaching 4, so we want the x is not too far away from 4. So the distance between x and 4 has to be small. How small is small? Well, less than delta. So we suppose the absolute value of x minus 4 is less than delta. And remember, we don't want x to be 4, so we put this to be greater than 0. Suppose this happens, then we hope to see that the distance between the function and the limit is less than epsilon. But we don't know yet, so we have to check it. So absolute value, this minus that, we have the 2x minus 3 and then minus 5. Now, hopefully this is less than epsilon, but we have to show it. Usually we can do some algebra. Right here you see minus 3 minus 5 is minus 8, and then we can factor out 2. Absolute value of 2x minus 8, factor out the 2, we can put the 2 before the absolute value, and then we still have that absolute value of x minus 4. Alright, this is okay, but we maintain this absolute value. And now check this out. Absolute value of x minus 4 is less than delta. Go back to this, and then we can rewrite this as less than delta, thanks to our assumption. So we have 2 times delta now. And keep in mind, at the very end, we want to end up with just epsilon. So by looking at this, delta should be equal to what? Well, it must be 2 on the bottom so that it can cancel with this 2, and then the epsilon on the top, yeah? So delta should just be epsilon over 2, and we can just come back here and put down epsilon over 2. And again, because epsilon is positive, that means our delta is positive, yeah? So this is legitimate. And right here, delta is epsilon over 2, so we write down equal, and this is it. Once we're done, make sure that you put a box and then shade this in. This is less than epsilon, all right? So that's the first one, and we have 23 more to go. So here we go. All right, let's get into some slightly serious business. Number 2, I have the limit as x approaching 5. And on the bottom, I have x minus 3. On the top, I have 1. And this is 1/2. It's a fraction case, right? So what do we do? Well, again, finite, finite. So this is, again, a epsilon-delta definition. Given epsilon greater than 0, choose delta. We don't know yet, just leave it. And then we are going to suppose the distance between x and 5 is less than delta, and make sure that it's greater than 0. And then we are going to check this minus that in the absolute value is less than epsilon. Here, let's do some algebra. And the way I like to do it is, let's just multiply the denominators. So we have 2 times x minus 3. And then I do this times that, which is 2. And then I do this times that, so I have minus x. And then minus 3, which is plus 3. So that's what we have. Still maintain the absolute value. Now on the top though, we see that we have 2 minus x plus 3, so that's minus x and then plus 5. We can factor out a negative, and the negative in the absolute value doesn't matter. So in fact, let's write this down. We have 1/2 is just a constant, so I'll keep it like this. And then again, this right here, I can write it as absolute value of x minus 5 after factoring a negative, but the negative doesn't matter in the absolute value. And then we have the x minus 5. And then we have the x minus 3 on the bottom, still in the absolute value though, so I'll just put down times 1 over absolute value x minus 3. Okay, so yeah, as I told you, once we have the reciprocal, we're getting to study more serious business. So what do we do though? Here, notice that we have absolute value of x minus 5. We can come back to our assumption here. We know that's less than delta. So that's very nice. So I'll just put down this is less than delta. And then we have a 1/2 at the front. And now the question is, what do we do with this though? 1 over the absolute value of x minus 3. It looks like we are stuck. Here's the thing though. Usually when we go from here to here, hopefully we can just have an expression in terms of delta. And then later on, we will be able to figure out what epsilon should be. We will be able to figure out what delta should be in terms of epsilon. But anyway, we need to have a bound for this. Here's how we do it. We want to have another condition on delta so that we can work with this inequality. Usually, let's just come back here right away and then put down minimum. And you can pick some numbers that you want. Easy enough number. Just 1. Usually works out really well. So I'm just going to pick 1. Sometimes 1 works perfectly, but not all the time. There will be an example that we cannot use 1, but that will be for later on. For now, let's put down 1. With that being said, we know that we can just look at this and say absolute value of x minus 5 is less than 1. Open this absolute value. We know x minus 5 is in between of -1 and 1. And then we need to somehow get to this. So right here, let's just go ahead and add 2 to everybody because we want to end up with x minus 3 somehow. So this is 1. And then we have x minus 3, and this is 3. Now we have this on the bottom and also the absolute value. So what should we do first though? I'll tell you, let's take the reciprocal first. So if we take the reciprocal, then we are going to get, notice they are all positive. The reciprocal of this is 1, and the reciprocal is just 1 over x minus 3. And the reciprocal of this is 1 over x minus 3, and this is 1 over 3. Because they're all positive, we can just flip the inequalities. Once we have this, take the absolute value. So I can apply the absolute value here. Absolute value of 1 doesn't matter, so we are just looking at 1 over absolute value of x minus 3. We'll just pick the bigger number, the one has the bigger absolute value technically. 1. We say this is less than 1, and then that's the bound that we want. Let me just show you though, what if you took the absolute value first? Imagine right here, if you took the absolute value, then you are saying that absolute value of x minus 3. Again, you pick the bigger number that has the bigger absolute value, which is 3. So you're saying that this is less than 3, which is true. And then if you take the reciprocal here, you are looking at 1 over absolute value of x minus 3, and you compare that with 1 over 3. Because they are both positive, and you will just have to flip the inequality. But what's wrong with this though? Well, remember, we want to show that this thing is less than blah, 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 and then epsilon at the end. We want to have less than. If you have a greater than here, you put it here, that's like they're fighting. Less than and greater than they're fighting. No, don't do that. It's like you're fighting with little brother or little sister. No, don't do that. So, don't do this. Right? This is not the way to go about it, but this is. So keep in mind, take the reciprocal first and then the absolute value. Then we can come here and say this thing is less than 1. We have a less than right here already, so I can just say put on the 1 like this. All right, now once we have an expression in terms of delta only, then we want to figure out what delta should be in terms of epsilon, so that we can end up with epsilon. 1/2 times what will be epsilon? Well, we know 1/2 times 2 epsilon will be epsilon. They cancel out very nicely. So we want the delta to be 2 epsilon, right? We want to have this condition as well. So we come here and then we put down 2 epsilon. So once you have the 1, you get to use this right here. And then once you have the 2 epsilon, you get to say this right here. Here's a small thing though before we finish, because we still have this thing, right? We still have that little part that we haven't filled in. What should we put down right here? We'll have a look. Not equal sign, because right here we are saying delta is the minimum of 1 or 2 epsilon. This or that. But either way, we know this is going to be less than or equal to 2 epsilon. All right? Because it's the minimum of this or that. So either way, it's going to be either equal to 2 epsilon or less than 2 epsilon. So delta is less than or equal to 2 epsilon. Right here, we put down less than or equal to. With all that, we are done. Put a box right here and shade it in. And let me tell you, the moment you put down the box and shade it in, this is much better feeling than you put down the plus c after you finish the integral. Trust me, right? So, number 2. Okay, continue. I don't know if you guys would disagree with what I said or not, but okay, to be honest, they both feel great, right? Plus c or the box, they both feel great. But I will give a slight edge to I will choose the box over the plus c all day, because it's just that. Anyway, number 3 here, the limit, and I will still give you guys the same function, still 1 over x minus 3. But this time though, we are going to take the limit as x approaching infinity. Of course, if you work this out, it's just 1 over infinity. The answer should be 0. How do we prove it? Here we go. Pf. The limit is 0, which is finite, so we use epsilon. We want to make sure that the distance between this and that is less than epsilon, right? So given epsilon greater than 0, choose. Well, x is approaching infinity, so don't do delta. We are going to use capital N. But what's capital N though? Don't worry, we don't know yet. Just write it down for now. We'll figure out later. When x is approaching infinity, we are going to write down suppose. But don't say the absolute value of x minus infinity. That doesn't make sense. X approaching infinity means that x is going far, far, far to the right. X is big enough. How big? X is greater than n, that big. If x is greater than n, then we hope to show that the distance between this and that is less than epsilon. Absolute value, and I will still write down our function, and then I'll purposely write down a minus 0, but we know minus 0 doesn't matter. So this is really just x minus 3 on the bottom, and then we have a 1 on the top. And now what though? Well, we are going to come back to our condition. We have x greater than n, so we have to somehow use this. Here's the thing. When x is greater than n and x is approaching infinity, right here, let me just put down a small condition. This is greater than 3. I want to have that. But can I really say so? Yes. This thing right here is going to be an expression somehow be greater than n. Be greater than 3, just trust me. But the reason I need to say they are both greater than 3 is because once they are both greater than 3, then we can say x minus 3 is greater than n minus 3, and they are both positive. And then we can take the reciprocal on both sides, and we get 1 over x minus 3, 1 over n minus 3. They are both positive, so we can just flip the inequality like so, and that's exactly the correct inequality that we want. You don't really need to do this all the time. If you know that x is greater than n is greater than 3, you can do the following. You know this is positive. you can just replace the x with n. So you write down 1 over n minus 3. Can we make a comparison? Yes. Because x is bigger than n, that means x minus 3 is bigger than n minus 3. If the denominator is bigger than the other one, and they have the same numerator, then the whole fraction here is going to be smaller than this fraction. So that's okay. Right? So you don't really have to write this down, but of course it helps. Now, we have an expression in terms of n. Just like earlier, you want to have an expression in terms of delta only, so you can figure out what delta should be in terms of epsilon. Right here, we can figure out what n should be in terms of epsilon. To do so, you just write it down on the side, 1 over n minus 3, you put it to be epsilon. Multiply this, divided by that, we know 1 over epsilon equals n minus 3. Add 3 on both sides, capital N equals 1 over epsilon greater than plus 3. The bird. Anyway though, you see, this is the n that we want. We want 1 over epsilon plus 3. I told you. So just note that, put that down for now and then hope for the best. So that being said, I'm just going to put this down for n. So we have 1 over epsilon plus 3 and then minus 3. Because n is equal to that, here it will be an equal sign. Work this out. Of course, we get epsilon. Done. Right? Done. So this is how you prove a limit when x goes to infinity. Alright, so let me know if you guys are really doing epsilon-delta definition or epsilon-N definitions, all that in your calculus class. Usually at the university, they will teach this, or if you are taking a real analysis class, which is upper level math class, then you do this. Or like an honor calculus class. Alright, number 4. Here is a limit, and again I'll still give you guys the same function, 1 over x minus 3. And another interesting number that we look at is if x is approaching 3 plus. If x is approaching 3 plus, this thing will approach infinity, right? No, just kidding, I put down infinity. I want to say infinity. Alright, here we go. The limit is infinity. So what do? We use big M, right? Given big M, because we want to show that the function is going up and up and up, bigger than any M that you can possibly set. So given M greater than 0, but x is approaching 3 plus, this is finite, so it's delta. We will say choose delta to be something we don't know yet, just leave it. Then we suppose, and now here's the deal. If we have x is approaching 3, this means we're looking at 3 in the middle, and we can go from the left or go from the right, delta distance away. So we can get 3 minus delta here, or 3 plus delta here, and x is somewhere in the middle. But that's when we have just a 3. Here we have a plus. If we have x is approaching 3 plus, this means we're just going towards 3 from the right hand side. So here's 3 coming from 3 from the right hand side. We just care about to have 3 plus delta, not the other side. So here I'm going to write down the distance between x and 3. So I'll write down x minus 3 is less than delta. And again, we don't want x to be exactly equal to 3. So put that down. You see the difference is that if you have x approaching 3 plus, you don't want the absolute value. When you have the absolute value, you go both directions. And of course, similarly, when you have x approaching 3 minus, that means 3 right here, and you go to the left only, right? So this 3 minus delta like this. Then in that case, you will write x minus 3 is in between of 0 and negative delta. Just from here to the left. Yeah, so that's the small difference. That being said, again, the key is play around with the inequality. Make sure that this time though, we want to get our function. So let's check it does happen. Our function is 1 over x minus 3. We want it to be going up and up and up. And you don't need absolute value. Going up is positive, so you want to have this. We want to show that this right here is bigger than our capital N that we said earlier. But I don't know yet. I cannot put that down. So let me erase. So what do we do? Well, don't worry. Sometimes this kind of limit can actually be easier. Here, x minus 3. It's in between of 0 and delta. This is positive. So can we just do reciprocal? Yes. Of course, just focus on this part, right? Don't do reciprocal for that. If you take a look at 1 over x minus 3 compared with 1 over delta, well, flip the inequality, we want a greater than. This time we want a greater than, and we do have the greater than. So we can right away say it's greater than 1 over delta right away. Very nice. And now when you have an expression in terms of just delta, you can just go ahead and set whatever that is to be whatever we put down earlier, which is capital M. So for delta in terms of N, delta is just 1 over M. Put it here, 1 over big M, and then put it here to finish. So we have this equal 1 over big M. Of course, this right here is just big M, and we are done. Told you, done. So far number 2 is the hardest one, right? But if you practice all this, seriously, after the 24 rigorous limit proofs, you will be able to write proofs as well. And your university calculus class or real analysis class will be much better, much more fun, all that good stuff. Okay, number 5. Here we have the limit. This time we have x approaching infinity, and we have 3x over 2x plus 1. This right here, x to the first power, so just 3 over 2. Nice. This is the question that you will love so much in your Calculus 1 class, if just the computation. But to talk about the proof, well, let's see. PF. This is finite, so use epsilon, yes. Given epsilon greater than 0, this is approaching infinity, so we use big N, yes. Choose big N to be something. Well, here we are going to suppose when x is bigger than big N, then we hope to show that this minus sign in the absolute value is less than epsilon. So absolute value, we have 2x plus 1, 3x, and then minus this. All right, do the algebra. So I'm just going to multiply this and that on the bottom. So 2 times 2x plus 1. And I will do this times that, which is 6x. And I'll do this times that, which is negative 6x, and then negative 3. I still need to put down the absolute value, but we notice this and that cancel. Absolute value of negative 3 doesn't matter, it's just 3. And then we have 2 and then 2x plus 1. Now, here's the thing. Do we need the absolute value? No, because if x is approaching infinity, then you hope that x is big enough, right? So let's just put down this right here is greater than 0. But technically, as long as it's greater than negative 1/2, it's okay. But I'll still just put on greater than 0. Because if this is greater than 0, of course it's greater than negative 1/2. With that being said, we don't need absolute value, and this is equal to that. Now, how can we proceed? Here's the deal. We know that x is bigger than n. If you replace the x with n, then you can get the following. You get 3 over 2 times 2n, and then plus 1. And that's great, because we can actually make a connection between this and that. This has to be less than that, because the denominator here is bigger than this denominator due to the fact that x is greater than n, our assumption here, and then the 3 is on the top is the same. Once you write this down, of course, when we have an expression in terms of n already, you can just do some scratch work on the side real quick, put that down, and then make it equal to epsilon, and then solve for n in terms of epsilon. But this is a little bit too much work, all the solving part. I'll show you guys something slightly better. Keep in mind, if you can write down each and every inequalities legitimately, then the proof is also legitimate. I have done a video going over the details on that, so check that out if you need to. So here we go. How am I going to do it? The bigger the denominator, the smaller the whole fraction is. Here we have 2 times 2x plus 1. Let's ignore the plus 1. Compare this at 3 over 2 times 2x. Can we say something about this and that? Yes, we can say this is less than that. Yeah? Sure thing. So as you can see, we can actually just say this right here is, let me just put down, less than 3 over 2 times 2x, which is 4x, like so. It's slightly easier, but you will see that this technique will actually be useful later on too, so just kind of get used to that. And now we know x is greater than n. So again, I'm just going to replace the 4 with n, and then we will get 4n right here. I will just say this is less than, oh sorry, I should do this for you guys. 3 on the top, 4 here, replace the x with n, and we can say this right here is less than that. Now with this right here, it's just in terms of n, 3 over 4n equals epsilon, and then solve it real quick. If you want, you can do the following too. 3 over 4 is less than 1. So it's actually okay to say this right here is less than 1, and then over n. So why not? So the easiest n to get is just 1 over n. You make it equal to epsilon, so n equals 1 over delta, 1 over epsilon. We put n to be 1 over epsilon. Epsilon is greater than 0, so n is greater than 0, so this is true. And then right here we can just say this is equal to 1 over epsilon, which is just epsilon. And then with that, we are done. This is less than epsilon, right? So just like that. All right, so we have covered pretty much all the situations, but there's one situation we haven't covered: x approaching infinity and then limits infinity. But that's coming soon. Let's do another harder one, I will say. Number 6. Here's a quadratic case, but that's when x approaching 2. And we have 3x squared. Work that out, you get 12. So finite. This is the classic epsilon-delta definition. So here we go. Start off by saying given epsilon greater than 0, here we are going to choose delta to be something. This is x approaching 2 without the plus or minus. So we say, suppose the distance between x and 2, and you keep it in the absolute value, is less than delta, and then right here make sure you also have that. We are going to check the function is close to the limit, in the sense that absolute value of our function 3x squared minus our limit. Hopefully this is less than epsilon. All right, algebra time. We can factor out a 3 and then x squared minus 4. X squared minus 4 can be factored here again. And here's the thing. The absolute value of a product is the product of the absolute values. So let me just say absolute value of 3, which is just 3. And then absolute value of the first factor, which is x minus 2, and then the second factor like that. So from here to here, it's usually pretty clear. You can just work that out real quick. All right. We want to change all the terms and somehow give a bound, right? We have this. We can use that right away. This is less than delta. So we can say that's less than. 3 is still 3. And this right here is delta. Pretty good. Now we have a small trouble. What do we do with this? Well, let's give delta some number so we can work with this inequality more, right? Same style. Put down minimum and let's use 1 again. It works. With that being said, we can look at this part and say absolute value of x minus 2 is less than 1. Open that, we get x minus 2 is in between of negative 1 and 1. And we want to get to plus 2, right? So let's just go ahead and add 4 on, not both sides, but like to everybody. So this is 3, and then we have x plus 2 here, and then this is 5. Now, apply the absolute value. Once we have this, we know absolute value of x plus 2. You pick the bigger number that has the bigger, absolute value. So less than 5. So once we have that, we can say this thing is less than 5. Perfect. That being said, 3 times 5 is 15. And to end up with epsilon at the very end, we must make sure that delta is 1 over 15 times epsilon. So put on epsilon on top. So I will come here, epsilon over 15. Close this. And we know this is going to be less than or equal to epsilon over 15. So this is less than or equal to, and then we have the 3, we also have the 5, and we see that they cancel out. We end up with epsilon. Perfect, just like that. All right, number 7. Here we have the limit as x approaching infinity, infinity. And we have a function in the square root. Square root of 3x plus 1, work that out, you get infinity. Because square root function in this case is an increasing function to infinity. Good. This is the first time that we are dealing with both infinity. So we use big M because of this infinity, and we also use big N. Yeah. First, we say given big M greater than 0. Secondly, choose big N to be something we don't know yet. Then suppose x is far away, right? Meaning x bigger than our big N. Big enough, right? Now check our function is also big enough, in the sense that our function is bigger than M. But how do we do it? Well, here is the thing. It's really fun. Check this out. Again, work with inequality. We have a plus 1 here in the square root, and we know square root is an increasing function. So if we just take away the 1, I can just say this right here compare with square root of 3x. This is bigger than that. That's true. So you can ignore the plus 1. In fact, if you really want to, because again, this is an increasing function and x is greater than n, you could have say square root of 3x plus 1 is bigger than square root of 3n plus 1. And then once you have this, set it equal to m, and then solve for n in terms of m. That's fine. But this is easier. And if you really want to, square root of 3 is bigger than 1. You can ignore the 3 as well. Should we do it? Sure, why not? This is bigger than square root of x, because square root of 3 is bigger than 1. And sometimes you can say, just denote that square root of 3 is bigger than 1. This is 1.67 something. So this inequality is still true. And you can also say, because square root is an increasing function, square root of x is increasing. So take away the +1, this is true. Yeah, so just like that. Now, again, because square root of x is increasing, I can just replace the x with n. So we have that, and then this is still greater than. Looking at square root of n, I can say square root of n, set it to be m. Solve it, n equals m squared. That's the n that we want, m squared. This is equal. We have the square root, we have the m squared, and this is just simplified to m. Done. Okay, so this is legitimate. You may see some people, they have different n. As long as all the inequality works, all the proofs, like, it's legitimate. Cool. Let me check if this is still recorded. Perfect. Number 8. I'm going to give you guys the same function again. Still, limit square root of 3x plus 1. But this time, let's take the limit as x approaching 5. Work that out, just 15 plus 1. 16, take the square root, we get 4. Alright, finite and finite. So epsilon-delta definition, given epsilon greater than 0, and then we choose delta to be something we don't know yet, leave it. Suppose absolute value x minus 5 is in between of 0 and delta, and we are going to check the distance between our function, square root of 3x plus 1 minus 4, right? This minus that. Hopefully, this can be shown to be less than epsilon. Now we're kind of stuck because how can we make a connection between this and that? Well, don't worry. Keep in mind our good old days back in the regular calculus, where you have to compute limits involving square root, such like this. The limit as x approaching, let's say, 5, square root of x plus 4 minus 3, and then x minus 5, something like this. What do? We multiply the top and bottom by the conjugate, right? Right here, let's do the same thing. So this is equal to, I will keep this as how it is, square root of 3x plus 1 minus 4. But on the top, I will multiply with square root of 3x plus 1 plus 4. And of course, we'll also divide that, which is the square root of 3x plus 1 plus 4. Yay. Work this out. Multiply this and that. Square root cancel. So we just have 3x minus 1. And then minus, this is just a minus b times a plus b. So it's minus this thing squared, which is 16. And if you look at the top, this is just 3x. Oh, sorry, it should be a plus 1. This is 3x minus 15. We can factor out 3. So this is equal to, we have a 3 right here, all the way at the front. And then we will have x minus 5. Keep it in the absolute value. Right? And then lastly, we still have this on the bottom. But notice that this is always positive when I should say non-negative. Well, yeah, non-negative. Plus 4 is always positive. So we have this over that square root of 3x plus 1 plus 4. So that is what we have. Pretty good. And how can we continue? We do have the x minus 5 in the absolute value, so maybe we can use this right away. But you know what? If you do that, sure, and then the bottom is going to be bothering us, right? So can we get rid of the bottom? Yes, and this is how. If you just ignore the bottom, compare this with the top part, which is 3 absolute value of x minus 5. Can we make a comparison? Yes, and in fact, this is less than that. Why? Check this out. We have this thing plus 4. The bottom, this is non-negative plus 4. For sure, is bigger than 1. Don't say bigger than 0. This is true because we can say square root of 3x plus 1 plus 4 is bigger than 1. Right? 1 is the key number here. Don't say bigger than 0. Here is the example. So suppose we have two numbers, let's say 2 and 2. But right here, if I divide by a number bigger than 1, let's say divided by 6, compare them. Which one's bigger? This one's bigger, so I can still maintain that kind of inequality. This is bigger, yeah? So that's what we want. But if we have two, let's say this is 1 and 2. Let's say we have 2 and 2. If I say, let's divide this by a number bigger than 0, why if I pick, let's say 0.5 or 0.1? This is a positive number. If I divide it by that, which one is actually bigger? This is actually bigger now, and that's not the inequality that we want, all right? So once you say this is greater than 1, you can actually ignore the bottom. So we can just focus on the top. Remember, the less the expression that you have, the easier the proof will be. So just kind of get rid of stuff once in a while. All right. With all that being said, of course, here comes to the best part. We have 3 times the absolute value of x minus 5. We know that's less than delta. So this is 3 times delta. At the very end, we want to end up with epsilon. So delta should be equal to what? Delta epsilon was 3. So I will just say this is equal to, the 3 is still here, but delta will be epsilon over 3. Cancel, cancel, done. Don't worry, I haven't forgotten to put delta to be epsilon over 3. Now it's done, just like that, just like that. And you might be wondering, what if this is minus? But let me tell you, actually think about it. Will this happen if this is a minus? When we're doing these kind of things, can we get a minus on the bottom? Think about it. The answer is no. Why? Because this is always a subtraction, so the conjugate is always a plus, so not possible. All right, number 8. Number 9. Let's go back to a linear case, but this time though, let's say x is approaching a negative number, x approaching -2, and then we have -3x plus 5. Work that out, you get 11. This is a epsilon-delta definition, right? So given epsilon greater than 0, we are going to choose delta to be something, and then suppose the distance between x and -2, so we'll write absolute value x minus -2, so become plus 2 like this. And then let's say this is in between of 0 and delta, and we hope to show that the distance between our function, which is -3x plus 5 and minus 11 like this. All right, can we do algebra? Yes. Plus 5 minus 11 is just -6, and we can factor out a -3. So you can say -3 and then x minus, sorry, it's -6, but we factor out -3, so this right here should be a x plus 2. Yeah. And then I'll still maintain the absolute value for you guys. But absolute value of -3 is just a 3. So we just need to look at 3 times absolute value of x plus 2. Absolute value of x plus 2, hey, we can use that. That's less than delta. So delta shall be, again, epsilon over 3, just like the delta that we used earlier. But it's just coincidence. So this is 3 times epsilon over 3, cancel. Oops, don't say this is equal to a box. You want to say this is equal to epsilon. Done. Let me tell you, I have never done this many epsilon delta proofs in my life, or rigorous limits proof. Yeah, today it's actually the second time, but it's the same questions. But anyway, number 10. Here, let's talk about this one. The limit as x approaching 3, and we have x over x minus 2. Work that out. We get 3 over 1, so it's just 3. Okay, this is finite, so epsilon delta definition again. In my opinion, epsilon delta definition could be the hardest one. But of course, sometimes it depends on the function. This is a little bit tricky, but have a look. Proof. Given epsilon greater than 0, choose delta to be something I don't know yet. Suppose the distance between x and 3 is small enough, meaning smaller than delta, but also make sure it's greater than 0. Check our function in the absolute value minus our limit. Hopefully this right here is less than epsilon. So let's just go ahead and just work this out. So we can just say we have the same denominator, just x minus 2. And then this is x. And I will do x times negative 3, which is negative 3x. I will do negative 2 times negative 3, which is plus 6. Still maintain the absolute value. X minus 3x is just negative 2x. And then we still have the plus 6. Good. I can factor out a negative 2. Absolute value of negative 2 is just 2. So let's just work that out right now. We have a 2 at the front. And with that being done, we will have x minus 3 left inside, right, factor. And then you just keep the absolute value. So absolute value of x minus 3. All right. So hopefully that's clear and all that stuff. And then lastly, we have the x minus 2 on the bottom. So I just say multiply by 1 over absolute value of x minus 2. This is less than delta. So we can say that's less than 2 is still 2. Delta is here. But what do we do with this? Yeah, we have done this twice already. Go ahead, come here and say delta is equal to the minimum, and then right here pick a number that you want. Earlier I told you let's use 1, so let's see what if we still use 1. So with that one right here, we can go here and legitimately say absolute value of x minus 3 is less than 1. Open this. X minus 3 is in between of negative 1 and 1, but we want to get to x minus 2, meaning we will just add 1 to all this. So we are going to get 0, and this is x minus 2, and this is 2. And the inequality stays. Now, what do we do? Remember, I told you guys to do what? Reciprocal on both sides first, right? And then take the absolute value. Just imagine, if I take the reciprocal, then I get a 1 over infinity. I mean 1 over 0. Can I do this? 1 over 0, and then this is 1 over 2, and then 1 over x minus 2. And it's like this. Well, it's arguably true, but like I need to find an actual number to bound it. So maybe I shouldn't take the reciprocal first. If I take the absolute value first, then what will happen? If I take the absolute value, then I'm looking at absolute value of x minus 2 is less than 2. Great. And then if I take the reciprocal from here, 1 over absolute value of x minus 2, great. 1 over 2, great. But this inequality becomes greater than, and we don't want that. We want to have just less than. So this is not what we want. And unfortunately, this does not give us any good number. So it's kind of like we're stuck. Think about why this time the 1 doesn't work. Got it? Okay, I'll tell you. The reason that the 1 doesn't work is that, remember, 1 is kind of like the distance from 3 away, right? X is approaching 3. So if you look at 3, if you go to the right, if you go to the left 1 unit, you're left 1 unit, what do we get? We get 2. What's x minus 2? 0. Doesn't work. So in that case, you see that the difference between 3 and 2 is 1. So in this case, 1 is a bad number to use. Don't use 1. So what do we do? Well, don't worry about it. Same strategy, but just use a different number. Let's say 1/2, 1/3, 1/4, 1/10. Up to you, but we'll stay with 1/2. Same idea. Once we put down the 1/2 here, we can come here and say that's 1/2. Open the absolute value, x minus 3 is in between of negative 1/2 and positive 1/2. To get to x minus 2, I add 1 to everybody here. Then negative 1/2 is going to be added with 1, so that's 1/2. X minus 2 in the middle, and that's 3/2. Perfect. And then we do the reciprocal, then it's perfect now. Reciprocal of this is 2. Reciprocal of this is 1/x minus 2. Reciprocal of this is 2/3. Flip the inequality like so. It's legit. Then I take the absolute value, 1/absolute value of x minus 2 is less than 2. Yay. So I come here and say this thing is less than 2. That being done, 2 times 2 is 4. So we know that to end up with epsilon at the end, delta better be epsilon/4. Come here, epsilon/4. Close this. And we know to put down less than or equal to, and let me just write down the 2 and the 2, and then cancel them out. So this is how we write the proof. So that when people read from the beginning to the end, say, wow, how did you know all this? No, I didn't know that ahead of time. We have to work it out and just leave this for now a little bit and try to figure out what this should be in order to write down a good proof. So, very nice question. Of course, I came up with this. Anyway, go. All right, number 11. Let's prove the limit as x approaching infinity 1/x squared, that's equal to 0. 0 is finite. It's okay. Let's just go ahead and start with, given epsilon greater than 0, here x is approaching infinity, so we say choose big N, and then suppose x is greater than n. Hopefully we can show that. We check absolute value of our function minus the limit is less than epsilon. Well, this time we can just take out the absolute value because minus 0 doesn't matter, and then x squared is, no, this thing is always positive. X cannot be equal to 0, so just always positive. Like this. Can we do anything? Yes. Here's the thing. X is greater than n. We can say that's greater than 0. You will see later it will indeed happen. Once we have this, you can just work this out real quick. X squared compared to n squared, they're both positive, so it's greater than. Take the reciprocal 1/x squared, 1/n squared. This is the inequality, less than. So we can say 1/x squared. We can say that's less than 1/n squared. Right? Or we can just argue in the sense that we know x is bigger than n, x squared is bigger than n squared, thus this whole fraction is smaller than this whole fraction. Or if you want to work it out like this, that's fine too. And once we have an expression in terms of just n, just put it down on the side, set it to be epsilon and solve it. So this means we have n squared equals 1/epsilon. 1/epsilon. And then take the square roots on both sides. N equals 1/square root of 1, just 1, so just that. Just the positive version, of course. Come here, 1/square root of epsilon. Of course, it's greater than 0. Of course, this is true. So that's equal to 1/square root of epsilon, and you square that, and at the end, you end up with epsilon. All right, now number 12. Here, let's prove the limit as x approaching infinity. Square root x minus 3, this right here will be approaching infinity as well. So how can we make this work? It's kind of similar to the square root example that we did earlier, but you'll see a slightly different. Here, pf, infinity use m, this infinity use n. So given big M greater than 0, choose big N, don't know yet. Suppose x is greater than big N, check our function, which is square root of x minus 3, is greater than m. Don't need the absolute value. So now what do we do? Can we ignore the number inside? No, this is minus 3, so I cannot say compare this with square root of x and then say that's bigger. Doesn't work. But don't worry, because this function is increasing function. So if x is greater than n, we can really just replace the x with n, and then the minus 3, take the square root. We know this is greater than that. This square root function is increasing. Right, so this is an increasing function. So you can do more calculus in that regard, but I think this is pretty clear. So once you have this right here, in this case, cannot really take away any numbers. So we are just going to set this square root of n minus 3 to be big M. Square both sides, and then plus 3 on both sides. So n equals m squared plus 3, and that's exactly all we need. M squared plus 3. Right? So right here we can just replace m squared plus 3 minus 3 and the square root, and this is equal to, work that out, you get big M. Done. Right? I think this is pretty clear. Sometimes some people may want you to, write it down as this is greater than 3, and then just work out, okay, x minus 3 is greater than n minus 3, greater than 0, and then you take the square root on both sides like this. So square root of x minus 3 greater than square root of n minus 3. So yeah, so it kind of depends. This might be even more clear, but that was pretty good too. All right. We're halfway done. Only halfway done. Okay. So it's probably going to take about 2 hours. Number 13. I'll give you guys a rather simple looking function. X approaching 2, and then let's talk about x to the third power for the first time. Plug in, you get 8. Finite epsilon-delta. Given epsilon greater than 0, we are going to choose delta, don't know yet. Then we are going to suppose the distance between x and 2. So absolute value of x minus 2 is in between of 0 and delta, and then we are going to check. This minus that in the absolute value somehow is going to be less than epsilon at the end. Okay, here we go. What can we do? Factor it, of course. So factor this as the difference of 2 cubes. We get x minus 2 as the first factor, and then let's just apply the absolute value for that. And then for the second factor, we get x squared plus 2x plus 4. This is good. That's less than delta. Done. But this thing, we have to figure it out a little bit. We can do the same thing that what we have been doing before, right? Whenever we have like an extra part that have like x, and we cannot really get rid of it right away. In that case, just come here and write down delta to be the minimum of something. Just use 1 because there's no worry at all for this. That being said, we can say this right here is going to give us absolute value of x minus 2 is less than 1. Open it, we get x minus 2 in between of negative 1 and 1. And you can think about how you can go from here to here, right? But I want to show you guys a little bit more. I'm just going to bound the x value. I will just add 2 to everybody. Right? Add 2 to everybody. That will give me x in the middle, and then this is 1, and that's 3. With that being said, we can say absolute value of x is less than 3. You can still try to square everybody and then add the 2x and then plus 4, something like that. But sometimes you have like a weirder function, then maybe you can also try this. But anyway though, here, this is how I want to do it for this time. Earlier I used this, yeah? But as we can see here, we have 3 terms and they are all adding. So I want to take the advantage of the so-called triangle inequality. Meaning, we can break this down as the absolute value of the first. Right? It's all adding. Then you can just say this thing is less than or equal to. Actually, let me just write down one more line to make it more clear. Absolute value of x squared plus 2x plus 4, right? And then this time, this is less than, I still have the delta here, but I will break it down by the triangle inequality. Absolute value of the first, yeah? But absolute value of x squared is the same as absolute value of x, and then square, so I can put that down like this. Then we add it with absolute value of this. The 2 can be taken out right here. And lastly, absolute value of 4, which is just 4, but I will still keep it as absolute value, like so. And this is the triangle inequality. So I'll just put this down right here for you guys. Because of triangle inequality, which says the following. For all real numbers a and b, when we have the absolute value of a plus b, this is less than or equal to absolute value of a plus absolute value of b. So technically, I should have put down less than or equal to. Less than or equal to, yeah, sorry about that. So it works wonder. Why? Because we know absolute value of x is less than 3. So right here, I can replace this as less than. Delta is still at the front, chilling. But when we see absolute value of x, we can replace that with 3. So this is 3 squared and then plus 2 times this right here, 3, and then this is just 4. This thing is equal to delta times. This is 9 plus 6 is 15 plus 4 is 19. All right? So thanks to that, this right here is just a number as well. So I think it's slightly easier unless you really want to square both sides right here, and then you add it. Yeah. Anyway, delta times 19, and you can just set this to be epsilon. You figure out what delta is, right? But usually this step is just pretty straightforward. This is just going to be put delta to be epsilon over 19, right? This is epsilon. Cancel, cancel. I will come here and then put a, oops, sorry, I shouldn't say equal. I will say epsilon over 19, and that should have been less than or equal to. Delta is less than or equal to epsilon over 19 whenever you use the minimum. So just like that. All right, number 14. Limit as x approaching 6, 1 over 2x, and we are going to add 1. Work that out, you will get 4. here we go, proof, epsilon delta definition. Given epsilon greater than 0, choose delta to be something we don't know yet. Suppose our distance, the distance between x and 6 is in between of 0 and delta, then we hope to show that the distance between our function, which is 1/2 x plus 1, and we're subtracting 4 like this, is less than epsilon. All right, do the algebra. This and that is just minus 1, so this is absolute value of 1/2 x. Sorry, 1 minus 4 is minus 3. All right, this and that, they don't look the same yet, but check this out. The coefficient right here is 1/2. We can factor that out. And when we do so, we will just have 1/2 at the front and an absolute value. And just think about it as 3 divided by 1/2. So we actually have x minus 6. So it still works. So we can say this is less than delta. Right? And then figure out what delta should be. And I will just tell you delta should be 2 epsilon because they cancel. So I'll just say 2 epsilon. Finally, write down the epsilon, box it. Just like that. All right. Whew, it's actually quite a lot of questions, a lot of writing for this. All right, number 15. Here, let's take a look at the limit as x approaching infinity. And on the top, we have x. On the bottom, we have x squared minus 1. Work that out, you get 0. 0 is finite, so we use epsilon. So pf. Given epsilon greater than 0, x is approaching infinity, so we want to choose a big N to be something. Then we are going to suppose x is big enough, meaning bigger than the big N. We hope to show the distance between our function and the limit 0 is less than epsilon. Minus 0 doesn't matter. Check this out though. You will just have x over x squared minus 1. How can we provide a condition here so we don't need to put down the absolute value? On the top, x should be greater than 0, but here we have a minus 1. So we really want to make sure x is greater than the square root of 1, which is just 1. Let's put that down for now so we can just ignore the absolute value. Now what? Can we factor it? This is x squared minus 1, so can we factor x minus 1, x plus 1? Maybe you can try it, but no, cannot do it. All right, I'm not going to do that. And then let's see. Can we somehow get rid of the minus 1 and compare this with just x over x squared? Yeah, we can compare, but this would be that being bigger than this though, right? So, that's not the correct inequality that we want, because when we have the epsilon greater than 0, we want to show this is less than epsilon. So that's the bad inequality. So what do we do? Well, here's the thing. Wouldn't it be nice if we can just somehow cancel the x on the top? Let's think about it. Or maybe you want to try right here and then replace all the x's with n's. So let's see, n and then n squared minus 1. Can we make a comparison? Is this less than that? I will tell you, not clear. Maybe not true, I don't know. Just no, why not? Here's the thing, if you look at this, yes, we can say square both sides first. I square everybody first. So x squared greater than n squared is greater than 1 squared. That's okay. And then minus 1 to everybody. That's x squared minus 1 greater than n squared minus 1 greater than 0. That's okay. And then I will take the reciprocal on this and that. And that's okay. And right here we have a greater than, they are both positive. After the reciprocal, this becomes less than. That's okay. But here's the thing. On the top I have x. On the top here we have n. But x is greater than n. The greater than and the less than, again, they're fighting. So I cannot just replace the x with, I cannot just replace the x right here with, I cannot just replace the 1 with x and then the 1 with n and then keep the inequality. That's not clear. That's no good. So let's go back to the idea that maybe we can somehow get rid of that x. How though? Well, on the bottom we have x squared minus 1. Wouldn't it be nice if we have an x right here as well? Yes, so that we can factor out the x. Earlier you don't want to factor out the x squared minus 1 right here. It doesn't really do you any good. But if you can somehow have x squared minus x right here, then we can factor out just x and then we can cancel out the x. And it's much easier, right? Because earlier, as I told you, the x on the top is bothering us. Now, can we compare this and that though? Yes. Check this out. They both have x squared. When you minus 1 here, compare with minus x, which one is bigger? In fact, minus 1 is bigger than minus x. Yeah. So the whole fraction here is smaller than that. Let's show you real quick. Here, we know x is bigger than 1. Just compare x and 1, yeah? And then you can square both sides. This is x squared greater than 1. No, I want to do it like this. Sorry, a little bit higher. Let's do this. X is greater than 1. Multiply negative on both sides, so negative x is less than negative 1. Yeah? Yes. And then if I add x squared on both sides, x squared minus x is less than x squared minus 1. Yes? And then if I take the reciprocal, I will get 1 over x squared minus x being greater than 1 over x squared minus 1. And of course, they are all positive. Because x squared is greater than 1, minus 1 is greater than 0. And this right here will be greater than 0 as well. So yeah, they're all positive. So this is okay. And as you can see, this is the same as saying 1 over x squared minus 1 being less than 1 over x squared minus x. Alright, so hopefully this is clear. Now, that being said, I can factor out the x and then cancel this out. I cancel this out. Perfect. Yeah. So let me actually put it down here. This is less than originally x over x squared minus x. And that's why I put down earlier and then factor out the x. And cancel this and that out. So I can just move this to that. And then I will erase this because that's just some algebra work. Right? So that's done. So this thing is equal to 1 over x minus 1. Okay? Now it's just this part right here. The rest is pretty straightforward. Because x is greater than n, I can replace this with just n. So, sorry, let me write it down like this. 1 over x minus 1. I'm going to replace the x with n. And because x minus 1 is bigger than n minus 1, so that means this whole fraction is less than that fraction. Now this expression is just with n, so we can just put it on the side. 1 over n minus 1, set it to be epsilon. We know 1 over epsilon will be n minus 1, and will be 1 over epsilon plus 1. So we'll come here and say n is 1 over epsilon plus 1. Put that here. I'll just say this is equal to 1 over epsilon plus 1 and then minus 1 altogether is equal to epsilon. Okay, done. Just like that. Perhaps I want to just be a little bit picky. I want to write down slightly better organization for you guys. This is less than n minus 1, like this. And with that, this is equal to 1 over epsilon plus 1 minus 1, which is just epsilon. Slightly prettier. My board is not big enough, otherwise I'll just write down everything in one line. Anyway, that's it. Okay, number 16. Limit as x approaching infinity, x squared plus 2x, that will give us infinity. All right, infinity, so proof given. This infinity tells us that we should use big M. That infinity tells us we should use big N, so choose big N. All right, suppose x is bigger than big N, then we are going to check our function is bigger than the big M. So we have 2x squared plus 2x. Both of this is bigger than M. All right, what can we do? Well, check this out. X is bigger than N, and we can safely say that they are both greater than 0. X squared plus 2x. You can ignore the 2x and you can say that's bigger than x squared. Is this inequality legit? Yes. You can also ignore the x squared and just put on 2x. Is this inequality legit? Yes. Which one is easier? Well, this one is slightly easier. So I'm just going to ignore the x squared. Yeah? This is in fact bigger than that, but we know 2 is bigger than 1. So I can once say this is bigger than just x. X is bigger than n, so this is bigger than n. And I want n to be bigger than, just how to do what? N is equal to m, done. This works. Because right here, if n is equal to m, I can say this is equal to m. And done. Yeah. Just like that. It looks weird, but it works. It's legit. Right? This inequality is true. This inequality is true. This is also true. And of course, lastly, thanks to my choice, right? N is equal to m, and we're done. If you really want to, you could have done it as this is bigger than n squared plus 2n, and then set that to be m. And yeah, if you do it like this, then n will be the best n for this proof, but you really don't need to. This right here is okay, and this right here is okay. Remember in my previous video, I mentioned it that you may have different choices in terms of expression wise for delta or for like the n, all that stuff, right? Okay, number 17. Limit as x approaching 1, x squared plus 2x equals 3. So let's practice another quadratic one. This is the epsilon-delta definition. Same function like earlier. So given epsilon greater than 0, choose delta to be something. Suppose the distance between x and 1 is between of 0 and delta. Check absolute value of my function x squared plus 2x minus 3. Okay, take a look right here. Can we factor it? Yes, we get what? X minus 1 times x plus 3. this is less than delta. Put that down right away. This, we need a number to work with, right? So go ahead and say delta is equal to the minimum of 1 and something. I don't know. By looking at this right here, we have absolute value of x is less than this 1. Open this, we get x minus 1 is in between of -1 and 1. And we want to go to x plus 3. So let's just add 3 to all this. No, add 4 to all that. 4, 4, 4. So this right here will be 3. This right here will be x plus 3. Oh, yeah. And this right here will be 5. Then absolute value of x plus 3 is less than 5. Yeah. Okay, so we can just say 5. So delta shall be epsilon over 5 here. So when you multiply by 5, they cancel. Come here, put down epsilon over 5, and close that brace, and then we write down less than or equal to. Done. Right, done. So hopefully, once you do these questions like many times, you'll see that, oh yeah, they are really not that bad. They are really not that bad. If you want to see some really bad ones, you can check out my other videos for like proving the product of the limit is the limit of the product. That was pretty bad. All right, let's do another one-sided limit. This is number 18. We are looking at the limit as x approaching 1 plus x over 2x minus 2. This will give you infinity. So here we go, PF. Infinity, we use positive big M, yeah? Given big M greater than 0. And you can imagine, I should also mention that if this was minus infinity, you just say given big M to be less than 0 to begin with, and later on you just flip the inequality. You can try that on your own. Given big M greater than 0, x is approaching 1 plus, so we'll use delta. So choose delta to be something. Suppose the distance between x and 1 from the right hand side, so no need for absolute value, just x minus 1 in between of 0 and delta, like so. We want to show that this is going to be greater than m, so hopefully x over 2x minus 2 is greater than m. Okay, what should we do? Check this out. Let me see, let me know if you think this makes sense or not. All right, x is in between of 1 and 1 plus delta, right? Because you can just add 1 to everybody. X over 2x minus 2. We want to show that this is greater than m, right? That's what we want to show. This is a minus 2. Can we just say that's greater than, ignore the minus 2, like this? Because this denominator is smaller than that, so the whole fraction is bigger than that. Cancel, and 1/2. This right here is legit. Don't get me wrong, this right here is legit, but this is not what we are trying to do. We are trying to make a connection between this and also the m. Alright? So don't do it like this. And the reason is because this time though, what we have is x minus 1, this expression. So we make sure we utilize that. Check this out. We know x minus 1 is positive and it's in between of 0 and delta. So right here, can we just take the reciprocal on both sides? This and that. So 1 over x minus 1 compared with 1 over delta, flip the inequality, that would be bigger. Yeah? So you can factor out the 2 like this. So we have x over, and we can factor out 2. Let's put it down like this. X over 2 times 1 over x minus 1. We know this is greater than 1 over delta, so that's okay. So we can say 1 over delta, and we still have the x over 2 like so. Now check this out. We know this part. 0 is less than x minus 1, meaning x will be greater than 1, yeah? If x is greater than 1, can I just replace that with 1? Like that? Yes. 1 times 1 is 1 over 2 delta. It's legit. Okay. Now, it's just an expression in terms of delta. So 1 over 2 delta, put it to be our big M, and just solve it. So multiply delta on both sides, divide the M on both sides. Delta equals 1 over 2m. So I will put that right here, 1 over 2m. And then replace that right here. That's an equal sign, 1 over 2 times 1 over 2m. 2 cancel. 1 over m equals capital M, just m. Yes, number 18. Let me check if it's still recording. Very nice. All right, it's number 19 and number 18. Moving on to number 19. Here we have the limit as x approaching infinity, x squared over 3x squared plus 1. That's 1/3. Finite, so we use epsilon. X is approaching infinity, use n. So here, pf, given epsilon greater than 0, choose n to be something. Suppose x is greater than n, and then we want to show that the distance between our function and the limit, hopefully this is less than epsilon. All right, so let's just work this out. Do the algebra. I'll multiply the denominators, so 3 times 3x squared plus 1. And I'll do 3 times that, which is 3x squared. And I'll do this times negative 1, which is minus 3x squared. 1 times that is just minus 1. Still, put that inside the absolute value. Cancel this, cancel that. Absolute value of negative 1 is just 1. And then, better yet, x squared plus 1, all that stuff, this is positive. So you don't even have to worry about anything. It's just always positive inside, so you can take out the absolute value. Perfect. Now, do you want to replace the x with n? If you want, yeah, but like I will wait. What I wanted to do is, I will say, I'll take out the plus 1 and say that's less than 1 over 3 times that, which is 9x squared. Just get rid of that 1. Easier that way. And 1 over 9 is less than 1, yeah? So I'm going to just say that's less than 1 over x squared. Okay? Now, right here, x is greater than n. You can be sure, it's going to happen. It's good. They're both positive, and of course, this means that I can replace the x with n, and then we can say this is n squared like this, and this is still less than that. To see clearly, you can square both sides here. X squared is greater than n squared. It's positive, and then you can see that the reciprocal of them, like so, told you. So now once we have this, go ahead, put it somewhere down on the side. 1 over n squared, make it equal to epsilon, and then solve it. So we are talking about n squared equals 1 over epsilon, n equals 1 over square root of epsilon. Of course, you just care about the positive version, so go ahead and choose that. And this is equal to 1 over square root of epsilon. Square that is epsilon, and then done. All right, number 20. Limit as x approaching 2 plus 1 over 3x minus 6, that will be positive infinity. Pf given m greater than 0, x is approaching 2 plus, so I will just say we choose delta to be something. Suppose it's just one-sided, right? So no need for absolute value. X minus 2 is in between of 0 and delta. Then we are going to check our function 1 over 3x minus 6 is bigger than m, right? And notice that x minus 2 here. Well, we better have the x minus 2. Don't just ignore all that stuff, right? Otherwise we cannot make the connection. So I'm going to just factor out the 3 right here. So we have 1/3, and then we have 1 over x minus 2. Well, we can see that they are both positive. If you take the reciprocal, 1 over x minus 2 compared with 1 over delta, this is bigger. So we can say this is bigger when we have 1 over 3 times 1 over delta. Yeah. So this is pretty much 1 over 3 delta. Put it to be epsilon, divide, multiply. Delta equals 1 over 3 epsilon. Put it here, 1 over 3 epsilon. This is equal to 1 over 3, and then we have 1 over 3 epsilon. This is not cancel, and 1 over epsilon is equal to epsilon. Done. Whew. I'm glad that I'm not doing like 100 of this. Alright, and by the way, if you know the reason for the number 24, leave a comment down below and appreciate that. Alright, you should know the answer if you have been watching my videos for like a 24 something. Yeah. Okay, let's do another quadratic one. Limit x approaching -2, and here we have x squared plus x plus 3. This is equal to 5. Alright, epsilon delta. Given epsilon greater than 0, choose delta to be something, and then suppose the distance between x and -2, so it's become +2 like this. And then we have between 0 and delta. Check the distance between this and that, so absolute value, we have x squared plus x plus 3 minus 5. Alright, do the algebra. So this is -2, so absolute value of x squared plus x minus 2. Can we factor this? Yes. I will put down x plus 2 first, and then x minus 1. This is less than delta, so we can put that down right away. This is the case that we have to come here and write down minimum, so we can use more numbers, right? This implies absolute value of x plus 2 is less than 1. Open this, x minus 2 is in between of -1 and 1. And we're trying to get to what? -1. So -3 to all this right here. This right here gives you -4, and then x minus 1, and this is -2. And here's the reason why I want to do another quadratic case. It's right here. We have -4 and -2. If I take the absolute value right here, which number do I choose? Do I choose the -2 because it's bigger than -4? That doesn't make sense because absolute value of whatever is always positive. So what do? you want to choose the number that has the bigger absolute value. In this case, it's -4. And then take the absolute value for that, so it's less than 4. Why? I just realized I haven't shown you guys why this works. I'll show you guys now. When you apply the absolute value to this, you see this is -4. This is -2. Of course, I can say that's less than 4. Then if you look at this, it's in between of -4 and 4. So I can say the absolute value of x minus 1 is less than 4. Okay, so that means delta should be epsilon over 4. Epsilon over 4. Close that, and then we have the less than or equal to times 4 cancel, and that's epsilon. Right. Four more. No, what am I talking about? That was question number 21. Three more. All right, 3 more. Number 22. Limit x approaching infinity. And we have x over 2x minus 8. And this equals 1/2. Here we go. This is finite, so we need epsilon. Yeah, you got it. Given epsilon greater than 0 and x is approaching infinity, so we need big N. Yes, you got it. So choose big N. Now we want to assume, suppose x is greater than big N, and we want to see that the distance between this and that is less than epsilon. So absolute value x over 2 times. Let me factor out the 2 for you guys. So 2 times x minus 4 minus 1/2, like this. All right, the reason I want to do that is so that you see you don't need to multiply the 2. The lowest common denominator is just 2 times x minus 4. This x, keep it, and then it's 2x times minus 1, so it's minus 2x. 2 times -4 is -8, yeah? So it's -8 times -1 is +8. Yeah? Yeah. Absolute value. All right, so this is minus x. No. What am I talking about? No. What am I talking about? Sorry. All right, I will just do this right here for you guys real quick. Multiply x minus 4. This is what happens when you are kind of tired and you're trying to do like basic math. All right, they have the same denominator now. So 2 times x minus 4. This is x. Distribute the -1, so it's minus x, and then minus becomes +4. Cancel. All right? 4 is positive already, doesn't matter. Oh, you know what? We can reduce this. That's kind of cool for the first time. So we just have a 2 right here. Over, we have x minus 4. Do we need absolute value? Well, you don't need to have absolute value if you come here and say that's greater than 4. Will it happen? You'll see. So that's what we have. And now, because x is greater than n, I'm just going to compare that with 2 over the n minus 4. X is greater than n, meaning x minus 4 is greater than n minus 4, and this will still be positive. So the whole fraction will be less than that, right? Unless if you want, you can do more work, but I think this is also pretty clear. All right, I'll do that for you guys real quick. So that means x minus 4 is greater than n minus 4 is greater than 0. So 1 over x minus 4, 1 over n minus 4 will be less than, yeah. and then it's still positive. Anyway, this right here, 2 over n minus 4. Again, once you have the expression in terms such as n, set it to be epsilon. Divide and multiply this thing, so we have 2 over epsilon equals n minus 4, and will be 2 over epsilon plus 4. Put it here, 2 over epsilon plus 4. Told you. Yeah. So this is equal to 2 over, we have 2 over epsilon plus 4, and after that we have the minus 4. Work that out, you will see this is going to be just epsilon. Yeah, 2 more. If you're still watching, or maybe you just skip the video to this point, I don't know. But if you're still watching, if you have been watching all the way, leave a comment down below. Let me know. I would really, really appreciate that. And you are fantastic. Seriously, you're awesome. You're phenomenal. Alright, number 23. Here, limit x approaching 3, 1 over, parentheses, x minus 3 square. This is infinity. This is a two-sided limit, but this is square, so it's infinity. It's like going up. Yeah, we have a vertical asymptote as 3. But here, let's go ahead and do the proof. Given big M, because we have the infinity, it's greater than 0. X is approaching 3, so choose what? Delta. Yes, you got it. Choose delta to be something. We don't know yet. Suppose the distance between x and 3 is between 0 and delta. Hopefully, we can show that it's bigger than m. So check our function 1 over x minus 3 square. Check this out. We have this thing right here, right? And this and that are both positive. We can just take the reciprocal. So we are looking at 1 over x minus 3 and 1 over delta, and you will get greater than. Isn't that exactly what we need? Yeah. Especially once we know they are both positive. I'm not taking the reciprocal of the 0 though. I'm just saying they are both positive. I can square this and square that, and I can still maintain the inequality. So this is 1 over x minus 3 square 1 over delta square. I still maintain the inequality. Yeah. So I can actually just say that's greater than 1 over delta square. Very nice, huh? Let's just put everything down in red. Alright, now in order to figure out 1 over delta square, put it to be m. Delta square equals 1 over m. Delta equals 1 over square root of m. That's what we want, 1 over square root of m. So this equals 1 over square root of m. And then we square that, which is just big M. One more. Yes, I know I didn't do anything with like a negative infinity. You should try that. Alright, number 24. Of course, you should know this is to honor Kobe Bryant. That's why 24. Limit as x approaching infinity, x squared over x plus 1. This is infinity because the degree on the top is bigger than the degree on the bottom. Alright, infinity, use m. This infinity tells you to use n. So pf given big M greater than 0, we are going to choose big N to be something. Suppose x is greater than big N, then we are going to check our function x squared over x plus 1 is bigger than big M. So what can we do? Can we just replace all the x's with n? So n squared over n plus 1 and say this is greater than that. Is this clear? Is this true? What do you guys think? Well, let's just do everything in detail to see if it's legitimately true or not. X is greater than n, and let's just put it greater than 0 for now, yeah? And that means I can just add 1 to everybody. So this means x plus 1 is greater than n plus 1. Okay, because I want to see that. And take the reciprocal 1 over x plus 1 compared with 1 over n plus 1. This is less than that. So you multiply by x squared, n squared. This inequality is not what we want already. We are stuck. So, no. No. So, what should we do? Hey, let's see. Earlier we said that, okay, x is greater than n, greater than 0. But what if we replace that with 1? And then we see that this is x squared. Of course, that will imply that x squared is greater than 1 squared. So can we say that's greater than 1 and over x plus 1? Yes, but the thing is that if you replace this x with n, then again the inequality will be fighting. No. So you cannot draw any. You cannot draw the conclusion that we want between this and that. This is actually smaller than that, so no. Whenever you write this down, remember the inequality should open the same way all the way, and the same direction all the way. So it's kind of stuck. So what do we do? Well, in this case, I really cannot replace the x squared with 1 squared. No, but let's check this out. What if we can somehow do what we did before? Remember there was a question, I forgot the number, it's like x squared minus 1, and you compare that with x squared minus x, and then we were able to factor out the x, and the reason is to get rid of the x on the top, yeah? Well, let's try to do this. Here's the deal. X is greater than 1. If I replace this 1 with x, let's see what will happen. X squared over x plus x. Can we make a comparison? X is greater than 1. That means this fraction will, this denominator will be bigger than this denominator, meaning that this will be smaller than that. Because, let me just say it like this. X plus 1, this denominator is smaller than this denominator. Thus, this whole fraction is bigger than this whole fraction. Alright? And if you want to work it out, of course, that's totally okay. So I'll just put this down on the side for you guys. We know x is greater than 1, so I can just add x on both sides. How's this? Yeah, and of course, once you add x on both sides, x is greater than 1, so of course positive. So I can just take the reciprocal now. This is x plus x over, 1 on the top and all that. 1 over x plus 1. Yeah? Flip the inequality, becomes like this. Yeah? So that means 1 over x plus 1 is actually greater than 1 over x plus x. That's what we want. And of course, we can multiply x squared, and this inequality is still true. So this right here is correct, and this right here is correct. So if you want to make it more clear, maybe you want to put it on somewhere. All right, so that's what you have. And of course, we can simplify this. This is just x squared over 2x. What's so good about this? Yeah, cancel, cancel. In fact, we're just looking at, let me write it down, x squared over 2x. Cancel, cancel. So we are really just looking at x over 2. Yeah. Whew. All right, now we know x is greater than n. So I will just replace this x with n, and then we have that over 2. So that's also clear. Then what should we choose for n? Go ahead and just write down n over 2 to be big M. N should be 2m, yeah? So n is 2m. So this n is equal to 2m. And then after that, divided by 2, cancel it out. Ladies and gentlemen, we get that big M. Yes! So, here you have it. 24 rigorous limit proof. And hopefully, this right here helps you with your calculus class or real analysis class. Proofs are not so bad. It's just practice a little bit. There are worse ones than this ones. Anyway, as always, that's it.